Hello friends and welcome back. In this video we'll be talking about accelerated frames of reference and the resulting phenomenon or concept of fictitious forces, not actual forces in the sense that we've been talking about up until now when we discuss forces, but in a slightly altered manner, in a way that I'm about to explain to you. Okay. All right. So up until this point, we have always done sort of a science and physics in particular, but all of science, and studied our phenomena in reference frame. We drew typically Cartesian axes, x and y. We also saw how to use polar coordinates if we want to go in that direction. But and we've sort of implied all along that we have studied the motion of objects in these in a reference frame, and in reference frames that are inertial. And the definition of inertial reference frame is kind of a circular, can seem like a circular argument, because the definition of an inertial frame is one where Newton's second law holds, essentially. And so one where, in particular, if the net force equals 0, then the velocity is a constant. As it turns out, if I choose a different observer, let's call actually this white one, let's call this reference frame S. If I choose a different observer with, different coordinate x, y, and y prime, this is system of reference S prime. Obviously, the two observers would disagree on the values of the coordinates, for example. See, this sees this point P in xp and in yp, whereas an observer in the second frame sees it as y prime p and x prime p, and they disagree on the value of those coordinates. However, they would not disagree that the acceleration of the point P is precisely proportional to the net force acting on the object, provided that, okay, so they both agree, both systems or reference frame agree, if and only if the relative motion of the two reference frame of S and S prime is linear uniform. So in particular, what this means is that if I look at the position vector that joins the centers of the reference frames, the origins of the reference frame O and O prime, that this vector here evolves with linear uniform motion. In simpler terms, if two reference frames have a constant velocity between them, and a classic example could be, for example, S is a person on a platform, on a train platform, and S prime is a person on the train. As long as the train is linear, uniform linear motion, then I'm okay. Then both observers, the person on the platform and the person on the train, they would see the same phenomena and interpret them in the same way. F equals ma for both of them. Okay. Now, this is obviously not the only thing that two reference frames can do. You can imagine it's quite likely, what if the train speeds up or slows down or takes a bend? Then it's no longer true that the origins of the reference frames are moving with uniform linear motion with respect to each other. And in that case, does f equals ma still hold? And the short answer is no, and the longer answer is no in very interesting ways that we're about to find out. So what can, actually let's delete this, what can reference frames do when it comes to any other possibility than uniform linear motion between them? Well, option number one, as I said, is that of a reference frame that moves with a an accelerated, a linearly accelerated motion. So if, for example, the motion of the origin, let's say v of O prime, is not a constant, and in particular, if there's an if not, it's not a constant, then for sure you will have an acceleration. And the other way where we can introduce acceleration is not with translational acceleration, but rotation. So imagine, for example, two reference frames that are at an angle, and this angle is changing. Then for sure there's an acceleration there as well, because we've learned that any change in velocity, not only in speed, that corresponds to an acceleration. A way to see this is, for example, imagine a point. As I said, let's actually let me draw this a little bigger. Give me a second. I'll delete this and start over. So let's say that we have these two reference frames that are at an angle with respect to each other, and this angle is changing. But let's start with this for now. So this angle phi, for example. Take a point P, and we call these coordinates y prime and x prime for the primed reference frame, and just x and y for the original reference frame. And as we did before, you can think of the coordinates that this point has in the two reference frame. Okay. And if you do it in the yellow reference frame, you would find these coordinates, x prime p and y prime p. So there's no doubt that they would disagree on the coordinates. We saw that that's not inherently a problem as long as the physics remains the same. But manifestly, this cannot be true, as we can see in a very trivial example of, let's say that P is at rest in the original system, or we called it S. Okay, that's the white reference frame, and we call S prime the one that's turning. If the S prime is rotating with respect to rotating, then for sure P is not at rest. Right? Imagine that the yellow axes move, for example, anti-clockwise, then definitely at some point the point P will cross the x prime axis and so on. And for sure the coordinates, the position of the point P is not constant in S prime. So an observer on the rotating reference frame would say, oh no, look, there's definitely some forces acting on P because it's not at rest and it's actually accelerating. You would see a circular motion of some sort. Now, how do we reconcile this with the fact that the net force is 0, as evidenced by this? We do that with fictitious forces. I'm about to tell you in a second what the various types of acceleration of reference frames, both rotation and translation, can do to the expressions for sort of the translation between the two reference frames. But conceptually, I want to just keep it general for a second and try to explain the concept and the key idea, and then we can do some more specific maths. So we clear the page, and let's rewrite Newton's second law in inertial frames. Where we know that the net force acting on an object is equal to the mass of the object and the acceleration. So far, so good. In non-inertial frame, in general, it's the acceleration as measured as seen from the primed reference frame is equal to the acceleration in the inertial frame plus some other correction, the form of which I'll show you in a second. But so there's a correction to it that depends on the translational motion and on the rotational motion. And so if we rewrite Newton's second law in this in terms of A prime, the acceleration in the non-inertial frame, we would see that the net force is equal to m times A prime plus this delta A that we have in addition to that. And so this immediately tells me two things. One is that an observer in the accelerated reference frame doesn't have an expression for so Newton's second law does not hold. So Newton's second is not true. And interestingly, the way in which this is not true allows us to rewrite this as F net minus m delta A as m A prime. So an observer sees, okay, I observe a certain acceleration in my reference frame. I multiply by the mass of this object. Then if I read the situation in the language of Newton's second law, I would infer that on the left-hand side here, there's a net force that is not just what an inertial observer would measure, but there's also a correction term, another force acting on the object that is causing the acceleration that I observe. This is not an actual force because it's not there as a result of forces acting on the object, but it's there as a result of the frame that I'm observing this phenomenon being non-inertial. And so this is called fictitious force or forces, in case there's a sort of several effects that contribute. So even before we go into the specifics of what these fictitious forces look like, we can understand the origin of these forces in quotation marks, as it's sort of what an observer in a non-inertial frame would use to interpret the natural phenomena that they observe, because the real external force acting is just not enough to explain the acceleration that is observed. Okay, so what is missing? Apologies. What's missing? That's the observer says, well, there's a fictitious force then acting on these objects. All right. In this next video, we'll be diving into the specifics of what these fictitious forces look like and what the type of relative motion of reference frames generates them. But for now, I'll thank you for your attention, and I'll see you soon.